Hello and welcome to Void Electronics. My name is Telian and in today's video I want to talk about number bases. More specifically, I want to talk about binary numbers and hexadecimal numbers because these are the most commonly used in electronics and programming. But first, let's talk about the numbers we use in our daily lives, the so-called decimal numbers. So at this point you may be wondering, okay, but why do we need to start with decimal numbers? We use them in our everyday lives so we know how they work, right? Well, yes, you're definitely right. However, with decimal numbers, we apply some rules automatically, without even thinking about them, and we need to become aware of those rules because those apply to other number bases to some extent. So in base 10, we have 10 possible values for every single digit, and those values go from 0 all the way up to 9, so we have a total of 10 digits. So let's break down a decimal number to see what it means. Let's take a number at random, for example 3496 in base 10. What does this mean? Well, the meaning of this number is right in the pronunciation in the English language. Sorry, French people.
3496.
So let's break it down. This means 3 times 1000 plus 4 times 100 plus 9 times 10 plus 6. And we can write it in a slightly different way, taking into account the fact that we have base 10 here. So we leave the 3 as it is, and then 1000 can be rewritten as 10 to the power of 3 plus 4 times 10 to the power of 2 plus 9 times 10 to the power of 1 plus 6 times 10 to the power of 0. And in this representation we've written our number based on the powers of our base, which is base 10. So if you take a look at the digits right here, this means that the rightmost digit gets multiplied by 10 to the power of 0. The next one gets multiplied by 10 to the power of 1, the next one gets multiplied by 10 to the power of 2, and the final one gets multiplied by 10 to the power of 3. So why is this relevant for us? Well, let's study a different base, for example base 2. So in base 2 we only have two possible values for our digits, 0 and 1. So now let's take a binary number and see how we can break it down. For example 1011 in base 2. What do you think this one means? Well, remember what we did here with the base 10 number. Here we have a number that is in base 2, so whatever digits we have here get multiplied by various powers of our base, which is 2. So the rightmost digit gets multiplied by 2 to the power of 0. The next one gets multiplied by 2 to the power of 1, the next one gets multiplied by 2 to the power of 2, and the next one gets multiplied by 2 to the power of 3. Looking at this, we can easily break down this number starting from left to right. So the first digit is 1 and it gets multiplied by 2 to the power of 3. Plus, the next digit is 0 and it gets multiplied by 2 to the power of 2, plus the next digit is 1 and it gets multiplied by 2 to the power of 1, and the next digit is 1 and it gets multiplied by 2 to the power of 0. And the final answer here is 11 in base 10. So what about hexadecimal numbers? Well, with hexadecimal numbers we have 16 possible values for every single digit, and those values go from 0 all the way up to 15. So at this point you may be wondering, okay, but how do we write a digit that goes all the way up to 15? Because here we have two digits instead of one. Well, that's because the first 10 digits going from 0 all the way up to 9 are the same digits that we use in base 10. So nothing new here. But what happens when we run out of digits? Well, we use the alphabet. So the next digits are A, B, C, D, E, and F. And you can make this table yourself if you want, and you can easily see what each one means. So after 9 we have 10, then 11, 12, 13, 14, and 15. So when we need to write down digit 10, we actually write down an A, and so on. And this is how this system works, which also means that we can have numbers that look something like this. So this is not really a word. This time coffee can actually be a number. So let's see what this number means. Well, I'm pretty sure this one will be a huge number, so I'm not that motivated to do all the math on video. However, I will show you how to break it down, and Then I will tell you the final answer. Remember what we did earlier with the previous bases? Once again, here we have to write the powers of our bases. The rightmost digits get multiplied by 16 to the power of 0.
The next one gets multiplied by 16 to the power of 1, the next one gets multiplied by 16 to the power of 2, the next one gets multiplied by 16 to the power of 3, the next one gets multiplied by 16 to the power of 4.
And the next one gets multiplied by 16 to the power of 5. And then we need to convert these digits to numbers. Digit C is actually 12. So this is 12 times 16 to the power of 5 plus 0 times 16 to the power of 4 plus 15 times 16 to the power of 3 plus 15 times 16 to the power of 2 plus 14 times 16 to the power of 1 plus 14 times 16 to the power of 0. I'm not going to do the math, but the final answer here is 12,648,430 in base 10. So now that you've seen how these numbers break down and how to convert them from their base to decimal, let's see how we can convert a decimal number to binary. For example, number 53. Well, to do this, we have to do repeated divisions by 2. So 53 divided by 2 equals 2. 2 times 2 equals 4. The remainder here is 1. 13. 6 times 2 is 12. And we have a remainder here of 1. Then we take 26 and divide it again by 2. So here we have 1. 1 times 2 is 2. 6. 3 times 2 is 6. And the remainder here is 0. 13 divided by 2 equals 6. 6 times 2 equals 12, and the remainder here is 1. 6 divided by 2 equals 3. 3 times 2 equals 6, and the remainder here is 0. 3 divided by 2 equals 1. 1 times 2 equals 2. The remainder here is 1. 1 divided by 2 equals 0, 0 times 2 equals 0, and the remainder here is 1. So even if it doesn't look like it, we've already converted our number to binary. So in order to see what this is in binary, we just have to read the remainders here in reverse order, starting from here. So 53 in base 10 is 1, 1, 0, 1, 0, 1 in binary. So to check this number, you can do what I showed you earlier. You can just write down the powers of 2 here and do the math, and then you should end up with 53 once again. So what about conversions from decimal to hexadecimal? Well, it's pretty much the same thing. We just have to divide the numbers by 16 repeatedly. So let's take our previous example, 53. And see what this means in base 16. So I will divide it by 16. Here we have 3. 3 times 16 is 48. And the remainder here is 5. 3 divided by 16 equals 0. 0 times 16 is 0. And the remainder here is 3. And now we have to read the remainders in reverse order to see what our number is. So 53 in base 10 equals to 3, 5 in base 16. What a weird coincidence. So what about conversions from binary to hexadecimal? Well, here we have a really nice trick that doesn't work with decimal at all. It just so happens that if you have a hexadecimal digit, all the values of that digit can be represented by exactly 4 bits. So you can easily group a binary number into groups of 4 bits, and you can convert each group individually into a hexadecimal digit. And the reverse process applies as well. So let's see how we can convert an individual hexadecimal digit to binary. Well, to do this I will show you another trick, and that is how you can easily write the first binary numbers. The first 16 binary numbers can be written like this. You can write 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Then you can write 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Then you can write 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. and then you can write 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1. That's how you easily write the first 16 binary numbers. Let's see what these are equal to. Well, these are equal to, let's write them in base 10 first. 0,
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14.
and 15. And now, based on the table that we made earlier, we can convert them to hexadecimal. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. So now let's take another hexadecimal number at random and convert it to binary. For example, C0FE. Let's see what this number looks like in binary. Well, we can convert every single digit separately. So let's start with C. If we go to C here, this is 11 and this is also equal to 1100. The next one, well, is just 0, so we have 4 zeros. The next one is F, that equals to 4 ones. And the next one is E, which is 3 ones and a 0. This is how you can convert a number from base 16 to base 2. And now let me show you how to count in the 3 bases that we studied today, starting with decimal. And I know what you're thinking, we already know how to count in decimal, right? Well, let's see what sort of rules we apply here, because those rules apply to binary and hexadecimal as well. So when we count in decimal, we go like this: 0, 1, 2, 3, all the way up to 9. We stopped here because at 9 something really interesting happens. And that is the single digit that we have here has reached its maximum value, the value of 9. So what do we do now? Well, we have to set this value back to 0. And then we have to increment the next digit to the left. So we get the next number, which is 10. And then we can continue counting by incrementing the rightmost digit. So we go to 11, 12, 13, and so on, all the way up to 19. And then the same process happens. The digit to the right is sort of full, so we have to reset it back to 0, and then we have to increment the next digit to the left. So we get number 20. Let's see what happens in binary. Well, pretty much the same thing, but we run out of values a lot sooner. The first number is 0, the next number is 1, and then the digit that we have here has reached its maximum value. So we have to set it back to 0, and then we have to increment the next digit to the left. So we get the next number, which is 10. Remember that the previous digit was 0, but we don't usually write that down. So now we can increment the rightmost digit and we get number 11. And then both of our digits have reached their maximum value, so we have to reset them to 0, and then we have to increment the next digit to the left, and so on. So now let's see what happens in base 16. We can count up normally, just like we did in base 10, up to a certain point. So let's start. It's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And now, with a single digit, we can go up to 10, but we don't write 10. We start writing the first letters of the alphabet. So now we write A, B, C, D, E, and F. Now we are at 15. So this is 10, 11, 12, 13, 14, and 15. So what happens next? Well, the only digit that we have here has reached its maximum value of 15. So now, once again, we have to increment the next digit to the left. So this becomes 1, and we have to reset this value back to 0. So now we have number 10, but this is not number 10 from decimal. This is actually number 16 in decimal. So now we can continue counting up. So we have 1, 1, 1, 2, 1, 3, and so on. We can go all the way up to number 1F, and after that, we have to once again increment the digits to the left and reset this digit to 0. So now we have number 20, but this is not 20, this is actually 32 in base 10. If this video clarified a few things for you, then please give it a thumbs up. And also consider subscribing to this channel if you're interested in more content related to electronics and programming. That's it for today. Bye. Because these are the most commonly used numbers in... But first, let's talk about decimal numbers, because these are... Hello and welcome to Void Electronics.